let's get started again. So, welcome back. It's my pleasure to introduce Fabio Ribeiro, who did his PhD in Lincoln and then has now moved to Imperial as a postdoc in Ben Glocker's group there. And in that group, they've been doing lots of really interesting stuff around causal ML for medical imaging. They're real sort of trailblazers in that area. So you heard a little bit about causality yesterday in the context of sort of large language models. I guess this is a different spin on causality in more of these kind of medical imaging models. So over to you.
Thank you very much. Hopefully you can hear me well. Good afternoon to everyone, and thank you all for coming. I'd like to thank the organizers as well for inviting me to give this talk on causality and generative models, which is something we've been working on over the last couple of years at Imperial, alongside these wonderful collaborators you can see on the screen. So let's get straight into it. Let me give you an outline of what I'm going to say in this talk. So I'm going to start with an introduction and motivation to causality. I'm going to try to convince you that it's something worth learning about and using in your day-to-day modeling. I'm going to cover basic things like the ladder of causation and structural causal models. I'll then move on to image counterfactuals. So counterfactuals are essentially hypothetical scenarios, so what-if type scenarios, and in this case applied to images. And then I'll present you some of the what we call deep causal mechanisms for structured variables, such as images, that we've been playing with. And then I'll touch on something called causal mediation analysis as well. And then finally, I'll show you some case studies on medical imaging, such as brain MRI and chest X-rays. And then I'll finish with some concluding remarks. Okay, so what is causality? As some of you are probably aware, that most of the scientific questions people usually ask are causal in nature. So I've got some examples here of causal questions you might ask. So how effective is a treatment in preventing a disease is one example. We've got, if I take this pill, will my headache be gone? And here's a more retrospective type of question. So would my grades have been better had I studied a bit more? So in summary, causality is simply the relationship between cause and effect. So let me give you this somewhat funny example, which comes from a study from the New England Journal of Medicine in 2012. And in the study they found that winning the Nobel Prize correlates pretty well with chocolate consumption. And you can see here the data's been plotted per country. And on the top right, we can see Switzerland eats the most chocolate and wins the most Nobel Prizes. So this is great news, isn't it? So if we take a look at Sweden, Sweden seems to secretly have the best chocolate, since they eat half as much chocolate as Switzerland and win just about as many Nobel Prizes. Things are looking kind of rough for Germany at the moment. So they eat a lot of chocolate, but they can't quite seem to convert the chocolate consumption into Nobel Prize wins. So what's really going on here? There must be some other explanation to this sort of correlation we observe that's so strong. So this segues nicely into something called Reichenbach's common cause principle. And it says in scenarios like this, when we observe some such correlations, one of three options is the case. So let's say the first option, chocolate consumption, truly does cause you to win the Nobel Prize. And we denote this by this C variable and then a directed arrow, and the N variable, which stands for Nobel Prize win. Second option is the opposite, so for some reason when you win the Nobel Prize, you start eating more chocolate. And the final option is both are actually caused by some unknown factor. In this case, we denote it as U. So U causes both chocolate consumption and Nobel Prize wins, and it induces this correlation between these two variables. Now, it remains to be seen which case this actually represents. But you could suggest things for this unknown factor, such as GDP per capita or wealth per adult. And the rationale being, maybe if you're a little bit more wealthy, you can eat more chocolate, and then maybe had a better education, and you're also more likely to win the Nobel Prize. But yeah, like I said, it remains to be seen which one of these cases is actually correct.
We need to withdraw chocolate from one of the countries, Stephen.
They won't like that. Okay, so now here's another study. So in this case, we had 2 treatments for kidney stones. So in both cases, so we have treatment A, treatment B, and in both cases we have 350 subjects. And we can see that treatment A has a higher recovery rate for both small and large kidney stones. So this percentage here is the percentage of people that recovered given the specific treatment. However, when we look at the average across small and large kidney stones, it seems like treatment B is better than treatment A. So this is a little bit counterintuitive the first time you are exposed to this, what's called Simpson's paradox. Because how can it be that treatment A is better for small and large kidney stones, but worse for both of them? So the reason is because stone size is a confounder. So what was happening was that patients with large stones, so the difficult cases, were being prescribed the better treatment, in this case treatment A, and the easy cases, the subjects with small kidney stones, received the inferior treatment. And when you aggregate the data in this way, it makes it seem like treatment B was more effective overall. So to really figure out which treatment is better, we need to make treatment independent of the size of the stone. And the real question we'd like to ask is, what's the recovery rate if all subjects were to receive treatment A versus treatment B? So the lesson here is that correlations may reverse depending on how we aggregate and filter our data. So we have to think very carefully about how we control for these types of confounders and how we aggregate our data and so on. Okay, so let's now take it back to something maybe a little bit more familiar to most of you, which is predictive modeling in terms of images, I'm saying. So given an image X, we're usually interested in training a model to predict some label Y. So we want to estimate this conditional distribution, P of Y given X. And the assumption is that we have efficient data pairs, and that the training and test data come from the same distribution. However, people don't usually stop to ask what the relationship is between the image and the label, and we argue that this is actually something that is very useful to think about. So we can have 2 options in this case. We can have a causal prediction task where we're basically predicting the effect from the cause, since X causes Y. Or we can have an anti-causal prediction task. So in this case, this conditional distribution, P of Y given X, is an anti-causal predictor, since we're predicting the cause from the effect. It's a little bit abstract, but let me give you some medical examples to kind of illustrate this. So imagine we have this skin lesion classification problem. We have some dermoscopic images In this case, we denote it with X. And Y is biopsy-derived diagnosis. So you can think of Y as like the ground truth underlying condition. So what do you think this predictive task is? Is it causal or anti-causal? Any takers? Correct. Brownie points. Yeah, so it's anti-causal because the biopsy was derived, the diagnosis was derived from a biopsy, not the image. So you can think of, there's some underlying disease that makes the image look a certain way, and it also made the diagnosis be whatever it was. So in this case, the relationship is anti-causal. So let's look at another example, in this case, brain tumor segmentation. So we have a structural brain MRI as the image, and then we have a manually drawn contour of some lesion or some tumor. So what do you guys think? Is this causal or anti-causal? It's not always super easy, but we would argue in this case it's a causal predictive task because the manually drawn contour is caused by the image, right? You get the image, then based on what the image looks like, or what the tumor looks like, you draw this label, this contour. So if you're estimating P of y given x, you can say that you're predicting the effect from the cause. And the final example, in this case, we have radiology reports. So we have chest x-ray images, and we have a diagnosis extracted from the report. Any guesses on whether this one's causal or anti-causal? Could be. So actually, we would say it's not clear. We don't really have enough information from what I've put on the slide because we don't know whether the diagnosis was derived from the image or from something else, from other lab result. So I guess it could be causal or it could be anti-causal. We need more information to establish these causal relationships. And actually this idea of meta-information is related to the data generating process, which is something we argue we should be thinking about when we want to handle the various types of shifts that can happen during acquisition or annotation or even selection. So if we want to be able to handle all these types of shifts, which can introduce different biases into our predictive models, we need to think about what the causal relationships are between these various aspects of the data generating process. Okay, so this segues into the ladder of causation. So De Sousa uses this sort of ladder with three rungs to help differentiate the different types of modeling, if you will. So the first rung of the ladder asks questions like, how would seeing X change my belief in Y? So this is essentially modeling correlations. So similar to the predictive modeling task I just mentioned, we're estimating conditional distributions, and we know that modern machine learning is pretty good at this task. The second rung has to do with interventions. So it asks questions like, what will Y be if I do X? So interventions are very useful for identifying causal effects, and they're pretty crucial for planning and policy making and figuring out the effects of drugs and so on. And the final rung has to do with hypotheticals. So we might ask questions like, what if X had not occurred? Then we can use counterfactual reasoning and that kind of more imaginative side of our intellect, if you will, to deduce causes of observed events. So we need a mathematical framework to represent and analyze all three rungs of the causal ladder, and the structural causal model serves that purpose. So a structural causal model, or SCM for short, is a triple. So it consists of two sets of variables, observed and unobserved variables. In this case, x are observed and u are unobserved. And then we have a set of functions, and these are known as causal mechanisms. Then the value of each variable x is simply a function of its parents or direct causes, and some unobserved variable, also known as exogenous noise. So let me give you a more concrete example of an SCM. It's a very simple one with two observed variables, also known as endogenous variables, and two exogenous variables. And these exogenous variables are called that because they're caused by factors which are external to the model. And endogenous variables are caused by variables in the model. Now the key thing to note is that because in this tiny SCM, x1 causes x2, it appears inside the mechanism of x2. So to get x2, there's some function of x1 and some exogenous noise term u2. In this case, it's just standard Gaussian, but it could be anything, maybe uniform or whatever, as long as it's exogenous or independent of the model in some way. So acyclic SCMs can be represented by what are known as directed acyclic graphs, or DAGs. And in these DAGs, we have edges that point from causes to effects. So what I mean by acyclic is simply that there are no cycles in the graph. So on the left-hand side, you can see that there's a cycle. And cycles give us all kinds of problems, which I won't go into today. It suffices to say that we're interested in acyclical graphs. So this is what we're going to be using, and what people use most of the time. And here are some common structures of graphs you might come across. So on the left-hand side, we have this x3 variable as a confounder, which is what we've already covered at the beginning. X3 in the second panel is a collider, so it's caused by x1 and x2. And in the third panel, we have x3 as a mediator, so it mediates the effect of x1 and x2. So x1 causes x2 directly, but also indirectly through x3, through this path. So we're going to be using this mediator sort of graph later on as well. So we'll come back to that. Okay, so SCMs with independent exogenous noise terms are called Markovian SCMs. And these Markovian SCMs induce a unique observational distribution over the observed variables, so these x variables in the graph. And then we have these Markovian SCMs satisfy this condition called the causal Markov condition, and it basically says that each variable is independent of its non-descendants given its direct causes. So SCMs can also predict causal effects of actions, and this is achieved by something called an intervention. So interventions answer questions like this. So we have that small SCM again. So For example, what would x2 be if we set x1 to some constant? So when we set x1 to some constant, what happens is that we replace one or more of the structural assignments or mechanisms. And in this case, we set x1 to some constant, so it no longer depends on u1. And when we do this, it induces a new submodel. In this case, I'm going to denote it as m subscript c. And the distribution entailed by this submodel is known as the interventional distribution, and it's generally different from the observational distribution that I just showed you earlier on. So we can manipulate things in this graph, in this SEM, and this changes the distribution of things that the SEM represents. So on the third rung of the ladder, we have counterfactuals. So SEMs can also help us consider these hypothetical scenarios and ask questions like, given that we observed some values of the variables x1 and x2, what would x2 have been had x1 been some constant c, for example? For a less abstract question, we can say, all else being equal, would I have been late had I not missed the train? And this kind of counterfactual reasoning or hypothetical reasoning is something we use quite a lot. At least I do in my day-to-day. Okay, so counterfactual inference involves 3 steps. The first step is called the abduction step. And in the abduction step, the goal is to update the distribution over the exogenous noise terms given some observed evidence. So we want to infer this posterior distribution over the noise given something we observed. The second step is the action step. So in that step, we perform some intervention. We set one or more of the variables to some desired quantity to obtain this submodel. And in the third step, we use this posterior distribution over the noise terms, which is compatible with the observations. And this submodel we obtained from intervening on something. And then we simply use those 2 things to compute counterfactuals. Again, this is pretty abstract, so I'll give you a very simple example of how we can compute a counterfactual in a tiny graph like this. So in this case, we have the same SCM, but I've defined the mechanisms as these very simple functions. So for x1, I said that x1 is just 1 plus u1. And x2 is just 3 times x1 plus u2. Don't worry about what u1 and u2 are at the moment, but just take these as given. And so here's the type of question we can ask, which is a counterfactual question. So given that we observed x1 is 2 and x2 is 4, what would x2 have been had x1 been 5? So all we have to do now is apply the 3 steps of counterfactual inference. And the first step is the abduction step. So we know that x1 was equal to 2. We observe that. And we also know that the mechanism for x1 is equal to 1 plus u1. So this implies that u1 must be equal to 1. Similarly, we know that x2 is equal to 4, since we observed that. And we know that the mechanism for x2 is 3 times x1 plus u2. So we just plug in the value that we observed for x1 here. So this is 2. And in this case, it implies that u2 is equal to negative 2. Another way to look at it is we invert the mechanism with respect to the exogenous noise term. So if we do this, it gives you, in this case it's very simple, so it gives you a closed form solution for this inverse mechanism, and would give you the same result, in this case 1 and negative 2 for the exogenous noise terms. So that's the abduction step done. we've inferred the values of the exogenous noise terms given some observed x1 and x2 terms. The second step is to perform the intervention in the question. So we asked, what if x1 had been 5 instead of 2? So all we have to do now is set x1 to 5. And in the final step, we just have to plug everything in to the mechanism of x2 and just compute the result. So in this case, we intervened on x1, so we put the intervened value into the mechanism of x2, and then we put in the inferred value of u2 into the equation as well. Multiply these two, subtract, and you get the result. So it would have been 13. And that's how you compute a counterfactual for a very simple query like this. Now the idea is we'd like to do this for high-dimensional things like medical images, to infer what-if scenarios and ask more interesting questions. But the sort of methodology is identical to what you can see on this slide. Hopefully that makes sense. If you come away with knowing only this slide, I'd be happy. Okay, so now this takes us into deep structural causal models. And these are essentially a way to leverage deep generative models to learn these mechanisms, these causal mechanisms that we mentioned. And these folks, some of my collaborators at Imperial, came up with some techniques that allows us to tractably estimate causal effects of interventions and perform counterfactual inference using deep learning models and so on. However, one of the challenges is that the abduction step is quite difficult for medical imaging problems because of the high dimensionality and sometimes the lack of data and so on. So one of the questions we've been trying to answer is whether we can generate high fidelity image counterfactuals, and if so, how do we evaluate these things? So let me give you some examples of the mechanisms we've been looking at, one of which is normalizing flows. And if you haven't come across normalizing flows before, they're basically a way to build complicated probability distributions via successive transformations of simple base distributions. So we can start with something like standard Gaussian noise. We apply some invertible function, and we do this many times. And eventually we end up at a very complicated function, density, which hopefully captures the density of our data. So let me give you a very simple example using two moons. So we start with a base distribution which is random noise, and then we have 4 or 5 transformations which squash it into the density of the two moons data set. So the long story short is that if we use normalizing flows, then we can have these invertible mechanisms do the abduction for us in a deterministic fashion. So we can invert this flow with respect to the noise to perform the abduction step in an easy way. And to train them, it's pretty straightforward. We use the change of variables formula, and we just maximize the likelihood. And it's also possible to condition on additional variables. So we can condition on the parents of x in this case, which could be whatever, depending on the scenario and the data you're dealing with. But the sort of one of the issues with at least discrete time normalizing flows is that for big images and multivariate settings, it can be sometimes expensive to compute this determinant of the Jacobian. So they don't tend to scale as well to images as they do to one-dimensional things. So here's another option we could use, a variational autoencoder. And it's a little bit better suited to modeling images But the caveat is that the abduction step is now non-deterministic, so we'll have to pay a price for this. So in this case, we can see the conditional flow that we just talked about in the panel below, and on top we have the conditional VAE. In this case, the bottleneck Z is acting as part of the exogenous noise for our image, so it will be part of the abduction step, which I'll explain in a moment. So to explain what the causal mechanism for X using this kind of conditional VAE setup, we basically have a causal mechanism made of two parts. So we have an invertible part, this H function. Then we have a non-invertible part, this G function. And this G function is just the decoder, so an arbitrarily complicated neural net that spits out a mean and variance, for example, over pixels. And then we assume that we have additive noise, and this H function is simply this sort of reparameterized sampling. So this H we can invert, it's just a linear function. But G we may not be able to invert because it's an arbitrarily complex neural net. So if we use this sort of setup, we have a factorized exogenous noise decomposition. So the exogenous noise for X has these two components, the latent code Z and some other epsilon which lives in observation space. So let me give you a very simple example of how we compute counterfactuals using this kind of setup. So like I said, the first step is to perform abduction. So in this case we have some image X, we have some parents of X. So in this case you can think of meta information about the image, things that you believe cause the image in some way. Then we have this encoder that maps from image space to latent space. So since we assume this Z variable is part of the exogenous noise for X, we forward prop X, get its encoding. Once we have that encoding, we need to infer the second part, so the epsilon. And this involves a decoding step and inverting this sampling mechanism in observation space. So all this really is you take the observed image X and you subtract the predicted mean, the predicted reconstruction, and divide by the predicted variance. And that gives you this epsilon noise. So now you have the two parts that you need. The second step is to, let's say we perform some action on the parents, whatever they may be. We set them to some new value. In this case, I denote it as PA wide tilde. And then all we have to do is forward propagate these new parents through the decoder, but using the same exogenous noise terms that we have abducted at the beginning. So the idea is you're only changing things about X that are dictated by the counterfactual parents and trying to preserve the identity of X as much as possible. And that's basically it. Hopefully that made sense. If you have questions at this point, let me know. Otherwise I'll move. Go on.
One question, for this thing to work, you need full information, right? So, for example, in your parents, you need to fully observe them. So, okay, so that it won't apply in a case where you say, for example, there's some missing information or something is poorly recorded.
Yeah, so ideally you have everything observed, but that's never the case. So you can't get away from making some assumptions. But let's say you do have some missing data sometimes. One thing you can do is you can try imputation. So you could try to infer some of the missing values, or you can say...
Are you talking about the parents? No.
Exactly. So you can think of these parents as like another graph. That's a way I'm denoting it as just one node, but you can think of it as a collection of nodes that describes some relationships between things, and some of these things will then cause the image. So you can think of like sensitive information about the image, and they may have relationships between themselves, but whatever those causal relationships are, you at some point have to make some assumptions, because you can't observe everything. If there are missing variables, you can try to infer some of the missing variables via imputation. So you could try to predict the values of the causes given the effects and so on. There's a few tricks using semi-supervised learning and so on. In those cases, that might be appropriate. Yep.
Implementation question. When you're training it, do we give BAX in the decoder and encoder side?
Yes. Exactly.
Actually, I have another question. How scalable is this in terms of patterns? Like, how many variables can you condition? Okay, it could be one.
Yeah, like you said, as much as you want. It depends on the dimensionality of the parents as well. If they're just like scalar, then you can have as many as you like. If the parents are other images, or even any other modality that's quite high dimensional, then it might cost quite a lot. But theoretically, you can condition on as many parents as you like, but be cognizant that the more parents you add in, the more difficult it will be to make them all interact with the model in a disentangled fashion. But we'll get to that. Okay. So one issue with the small-scale VAEs I just mentioned is that they don't really scale to high-dimensional images as well. They basically give you somewhat blurry samples and so on. So we need something else if we want to produce high-fidelity, high-resolution image counterfactuals. And one natural thing to try is a hierarchical VAE, which is essentially an extension of a VAE to multiple layers of latent variables. So instead of having only one latent variable Z, we might have a chain of latent variables. And this has been shown to improve the flexibility and performance of these VAE type models. The goal is basically the same. We have some generative model. In this case, it factorizes across these layers. And we want to optimize some model P to be close to the data distribution by maximizing this elbow function. It looks basically the same as the normal VAE one, except that we have a whole bunch of latent variables instead of only one. So there's been some work making these hierarchical VAEs very, very deep and very efficient, and it seems to have somewhat plateaued on this sort of architecture, which uses what's called a top-down inference model. Don't have too much time to go into the details of these two, but if you're interested, definitely check out these two works, which is basically what we based our hierarchical VAE models on. And if you want a little bit more of a historical look at the ladder variational autoencoder paper, and also this one. Okay, so quick detour to connect these things to diffusion models in case any of you are interested or know about diffusion models but not so much about hierarchical VAEs. So you can think of a diffusion model as a type of hierarchical latent variable model, but it has a set of very specific properties, one of which is that the encoder is fixed rather than learned. So in an HVAE, we want to learn representations of the data at different levels of the hierarchy. The diffusion model doesn't really care about learning representations. It's all about the generation. So you can think of having a fixed encoder rather than learning an encoder. Second property is that each latent variable has the same dimensionality as the data, which isn't necessarily the case for hierarchical VAs. And the third one is that we use a single model across all the latents in the hierarchy, which again isn't the case for the VAs. And this leads to lots of speed ups and so on. So without going into too much detail, we can show that the diffusion models maximize the elbow, but with a specific weighting function in front. And this elbow is essentially the same as what the hierarchical VAE one optimizes, except that some of these terms get cancelled out. But again, we end up with a very simple form of these KL terms. They simplify like this, and they have some weighting function in front. So that's basically the gist of it. They're very similar, but the winning recipe so far is the diffusion one. Okay, so let me give you a little bit more detail about the conditional hierarchical VAEs we've been using. So we played around with two generative model structures. So in this case, we have something we call the exogenous prior generative model structure. And all this means is that in this graph here, the latent variables never get to see the parents. So they're independent of the parents. They're exogenous to the model. And this sort of hierarchical structure just represents the generative model and the inference model that we used. In this case, it's 3 layers, but it could have been a lot deeper. The second option is a conditional prior. So in this case, the latent variables are conditioned on the parent values. And this gives us some other neat options and gives us some guarantees in terms of the latent variables we get, which I don't have time to go into, but there's reasons why we should use the conditional prior. And in terms of the actual architecture itself, pretty standard. You just stack a bunch of residual blocks, and you predict some Gaussian distributions over these latent variables at each layer in the hierarchy. We tried a couple of different options, but they're basically the same. One is a bit more expensive than the other. Any questions on this bit? Happy? Okay, so the interesting thing that we noticed about the conditional prior is that it induces a different type of model than the ones that people had been using before. So when we use this conditional prior, it induces what we call a latent mediator, since the latent variables are no longer exogenous to the model, since they're caused by endogenous variables. They're caused by observed variables. However, there's still an interpretation we can come up with that says that the resulting graph is still Markovian. So on the right-hand side, we've got what's called a twin network. And a twin network basically represents the observed things on the left-hand side and the counterfactual things on the right-hand side. So we can see that we have some image X that's observed, some parents observed. Then we have X tilde and PA tilde that are counterfactual and not observed. So in both cases, there's also these latent variables which are now a mediator between the parents and the image. And we also have a counterfactual mediator, which is a mediator between the counterfactual parents and the image. And the cool thing about having this sort of setup is that it can let you do something called causal mediation analysis. And causal mediation analysis, in the general sense, is defined like this. This is basically the study of how a treatment is mediated by something else. And it can help explain why or how individuals respond to treatments or stimulus. So in our scenario, it amounts to basically enabling some estimation of what's called direct, indirect, and total effect. So we can see what the direct effect of the parents is on the image. We can see what the effect of the parents through the mediator is on the image. And we can see what the total effect of the parents and the mediator is on the image. And these can be computed with these equations, which is essentially a difference between, for the direct effect case, is the difference between conditioning on the counterfactual parents and not. Indirect effect is the difference between conditioning on the counterfactual mediator and not. And the total effect is both of them combined. So the total effect should be equal to the direct plus the indirect effect, which is what we observed in our initial case study using a dataset called MorphoMNIST. So in this case, we controlled the data generating process, which follows this causal graph. It's pretty simple. Y is the digit label, I is the intensity of the digit, and T is the thickness of the digit. And we have that thickness causes intensity. And we were able to generate some data with this graph. And now we want to model these relationships using these deep mechanisms I've mentioned. So in this example, we have an original, in this case, digit 4 from the data set. And each column is an inferred counterfactual of the digit, as well as the intensity and the thickness. Now, the thing to note is that when we intervene on the thickness, we can see that the intensity changes. But when we intervene on intensity, the thickness doesn't change. So it respects the causal graph. And that's sort of the idea. If you want to see this in action, check out this Hugging Face demo. It should still be up. So here's a slightly more interesting case using high-resolution brain imaging. So in this case, we also start with a causal graph, but it's not known to us. In this case, the causal graph is assumed, and it's based on medical knowledge. So it's a medically informed assumption, but it's still an assumption. And we have a selection of variables. So in this case, we have M, which is the MRI sequencing variable. It basically says whether it's a T1 or a T2, and different sequencing makes the scan look different, basically. We also have ventricle volume, age, brain volume, and sex. And all these causal relationships are medically informed. So we know as you age, both your ventricle volume and brain volume are affected in some way. In fact, as you get older, your ventricle volume increases and your brain volume tends to decrease. Okay, so same as before, we start with some observation in the data set. In this case, it was a T1 scan of a 60-year-old male with a specific brain and ventricle volume. And each column is an intervention on one of these attributes. And the key thing to note is that we observe sharp counterfactuals with localized changes based on what the intervention was. So if we intervene on ventricle volume, we don't expect much else to change, since in the causal graph it doesn't cause anything else. But when we intervene on age, for example, we expect ventricle volume and brain volume to have some kind of effect. So these interventions follow the graph, and it's also possible to observe what the direct effect is. So in this case, you can think of this as just what's changed. So if you went from this observation to the T2 equivalent, this is what changed when we perform the intervention. And the bottom row is a sense of counterfactual uncertainty. So which bits in the image are we least certain about when we're changing things? And this can possibly be used as a way to figure out if you can trust the counterfactual or not. But there's better ways, which I'll get to a bit later on. Here's another example, in this case using chest X-ray imaging. And in this case, we used Mimic. We didn't have as many interesting variables or interesting causal relationships we could use. But in this case, the most interesting one is that age causes disease. And disease in this case is pleural effusion. And essentially, as you get older, you're more likely to get pleural effusion. We also have sex and race. And again, we start with some observation. In this case, a black 45-year-old male with no disease. And each column is an intervention on the individual parents of the image. And again, we observed localized changes that preserve the identity of the original subject. So they're not random samples. They are essentially answering what this particular person would have looked like if they had the disease. Okay, so you might be wondering, how can we trust these counterfactuals? Is there a way to evaluate them? Are there any theoretical guarantees that they're correct? Can we trust them in some way? And this is a very difficult question to answer, but we made a little bit of progress. So in this paper, we looked at measuring some axiomatic properties of counterfactuals, and it makes use of these two theorems, which are kind of old at the moment, but still useful. So the first theorem is the soundness theorem, and it says that there's three properties: composition, effectiveness, and reversibility. And these properties are necessary in all causal models. And the second theorem, called the completeness theorem, says that these properties are sufficient. And in this paper, we propose a way to use these axiomatic properties and propose a way to measure them as some sort of evaluation strategy for counterfactuals. So let me go into a little bit of detail and give you an example of what these different axioms are about. So the composition axiom, we have the definition here. It says that if we intervene on a variable to have a value it would have had without the intervention, then it shouldn't affect anything else. So you can think of this as our ability to perform null interventions, or our ability to reconstruct images or any data modality. And a model with high composition will be able to reconstruct the image iteratively without losing the identity of the original subject, or in this case a digit. And a biased model with low composition will not be able to reconstruct the image very well, and in fact, if you just keep iteratively reconstructing, it will lose more and more of its identity. So the second axiom, the effectiveness axiom, says that if we intervene on a variable to have a specific value, it should take on that value. So we can think of effectiveness as when we change, for example, an 8 to a 0, Does it change to a 0 in fact? And does it preserve other qualities? So for example, is the color preserved? Or does it lose properties of the subject? Now, effectiveness is quite tricky to measure because it relies on some kind of pseudo-oracle, like a classifier or a regressor, to tell if the intervention was effective or not. But nonetheless, in some cases, if we can measure effectiveness very well, then it should be a reliable measure of soundness. And the final axiom is reversibility. So the definition is a little tricky, but you can just think of this as cycle consistency. So how well can you go back and forth between your interventions? So if we start from a 6 and we go to a 2, how well can we go back to the original 6 and then back to that 2 and so on and so forth? So a model with high reversibility will be able to do this and essentially preserve the identity of the original image very well. And the low reversibility model will not. So it will lose the identity and possibly other properties of the original image. So one slight thing I should note is basically if you have a DAG, that's truly a DAG, and there's a theorem that says that composition, that this reversibility follows from composition in DAGs. So you may not need to measure this if you're confident that your DAG assumption is correct and so on. Okay, so then we identified that there's an inherent trade-off between these properties, and I don't know if this can be overcome, but it's something to be wary of. So if we want to be able to reconstruct things better, then usually we pay a price in terms of effectiveness, and vice versa. Okay, that's basically it for me. So to summarize, deep SCMs can generate high fidelity counterfactuals, and they're, as measured by axiomatic soundness, they're doing pretty well. I didn't have time to show you some empirical results, but if you're interested, definitely check out the papers. And we're also able to estimate direct, indirect, and total causal effects for these high-dimensional structured variables, which people haven't played as much around with. Causality is usually applied to lower dimensional things. So some big limitations are that we only consider these Markovian SCMs, and although it's quite common to do this, it's also quite a strong assumption in a lot of cases. So there's possibilities to extend to other scenarios. And also measuring this effectiveness axiom is pretty tricky because it requires separately trained classifiers which can have their own biases and so on. So definitely need to be careful with that. So some ideas for future work. Some of these we've already started tackling. So one idea is to use counterfactuals for targeted data augmentation. Instead of sort of random data augmentation, we can use something a little bit more intelligent and hopefully improve the robustness, sample efficiency, and fairness of these deep learning-based models. Second one is along the lines of the mediation analysis I've already shown you, and using those direct, indirect maps as some sort of causal explanation. And there's also opportunities to improve counterfactual soundness, either using medical guidance or additional machine learning techniques, or even different deep causal mechanisms. One big one is continue to provide more theoretical results of identifiability. So this means some guarantee of uniqueness of our counterfactual estimates, or guarantees of correctness, under some mild or at least plausible assumptions. Not always testable, but if testable, then even better. And lastly, extending these Markovian SCMs we've looked at to semi-Markovian settings and non-Markovian settings as well. This is a big open area. So that's it from me. Thanks very much.